Good evening, everyone. Good evening, everyone. We will be starting in 5 minutes. We'll wait for other participants to join, and after 5 minutes, we'll be starting the session. So, meanwhile, if anybody of you have any question regarding our previous classes, they can ask. We'll be starting in 2 minutes. Meanwhile, if anybody of you have any questions, they can ask. We'll sharply start in 2 minutes. Okay, everyone. So good evening, everyone. So my name is Varad Dau. So I am a PhD student at the Department of Chemical Engineering at Kanpur. I am also a PMRF fellow, and I welcome you all to this fourth week in this lecture series, in which I am taking in this problem solving session, in which I am taking couple of problems, which will help you in solving the assignment questions. And this is a weekly problem solving session which I am taking. So I would like to thank the NPTEL team for allowing me to carry out this activity. So before starting anything, I would like to ask if anybody of you have any question, they can ask, uh, or regarding the previous sessions which we have. Otherwise, we'll begin by this week's questions. Okay. So nobody has any questions, so I will start with today's question. So the first question which we have is that a binary mixture. Remember, when we say a binary, that means it is two components. Okay. So binary gas mixture. A binary gas mixture containing 25 mole% A and 75 mole% B at 50 bar total pressure and 100 degrees Celsius of temperature. The fugacity coefficient of A and B in the mixture are respectively 6.65 and 0.9. What is the fugacity of the gases? What we basically have is, we have a container. This container is filled with a binary mixture of A and B. Let's say the components are A and B, and it is at a total pressure of what? It is at a total pressure of 50 bar. Okay. Then temperature is 100 degrees centigrade. Okay. And the mole fractions. So remember, these are the mole fraction and not the mass fraction. So the mole fraction. So it's a gaseous mixture. Okay. That means Y and YB are given. So conventionally we use Y for gas phase mole fraction, whereas we use X for liquid phase mole fraction. So as it has been mentioned that it's a complete gas. So the mole fractions are vapor phase mole fraction. So Y is given as 0.25 and YB is given as 0.75. Okay. the fugacity coefficient of A and B. So we are given fugacity coefficient. Fugacity coefficient phi A and phi B has been given as 0.65 for A and 0.9 for B. Okay, and then we are asked for what is the total fugacity. Total fugacity is equals to what? Total fugacity of the mixture. Excuse me. Total fugacity of the mixture is what? Okay, so this is the problem statement. So anybody has any question in understanding the problem? The problem is clear to everyone. Okay, so I'll give you a couple of minutes to try the problem, and you can guess the answer. You can give me answer, and you can check. Anybody has any question in understanding? No. So let us discuss this. So the options for this, the options are for the options are 18.2 bar, 22.3 bar, 41.5 bar, and 33.8 bar. Okay, if any try once. Excuse me. Anybody got any answer? Anybody would like to try? Okay, so I will remove this. Okay, anybody will try the answer? The correct answer is option C, 41.5 bar. Anybody got it? Nobody got it? So let us discuss the question. Okay, the solution is, so we know that fugacity of a mixture, let us denote it by F mix. It is given by phi A into phi B into PT, where phi A is the fugacity coefficient of component A in a binary mixture having a mole fraction of Y. Phi B is the fugacity coefficient of component B in a mixture having a mole fraction of YB. For gaseous mixture, remember we are talking about gaseous mixture, because that is only fugacity mix gaseous mixture. Okay, this has been given to us in question. And P, here P represents the total pressure. P basically is total pressure. Okay, so this is the expression to calculate it. We are already given that pi is 0.65, pi b. So here there is correction. Pi b is 0.9, pi b is 0.9, pi is 0.65, pi b is 0.9, y is 0.25, and yb is 0.75, and we are also given total pressure. So we just have to substitute this known values into this expression. Okay, this is given as, this is not 0.65, this is 0.9. Okay, pi b is 0.9. So once we substitute this expression, these values into this expression, what we get is F mix equal to 0.65 whole to the power y, right? It is the expression multiplied by phi b whole to the power yb multiplied by total pressure. So when you solve this expression, it comes out to be around 41.5 bar. Okay, so the answer is fugacity of the mixture is 41.5 bar, which is option C. Okay. Anybody has any questions? Anybody didn't understand? Do you have any doubts? You can ask. Okay. The solution is clear to everyone. Anybody got the answer? Nobody got it, the answer. So you now know the correct answer is option C, 41.5 bar. Okay. I'll wait for a couple of minutes. If anybody has any questions or anybody would like to write this down, and then we'll move on to the next question. Okay. Anybody has any questions? Nobody has any questions? We'll move on to the next question. The next question which we have is this. It's a conceptual question. Okay. The question is, in a binary solution, again, in this course, most of the time you'll find that the problem statement will always have a binary mixture, but it is not essential that we use it. So why we are using binary is because it's easier to do the calculation, whereas the similar whatever concept we are using for binary mixture can be applied to ternary or quaternary or multi-component mixtures as well. Okay. So what we have is, in a binary solution, if molar volume of one of the component increases with concentration, the molar volume of the other, it decreases, it remains constant, or it increases, or it does not change. Let us understand the question. So what we have a binary solution. What we have is, here is a mixture. Okay, we have a binary solution in this. Okay, this has a component A and B. Okay, A plus B and molar volume. So what is molar volume? So it is molar volume or partial molar volume. Okay, I think it has to be partial molar volume. Okay, V1 bar. It has to be partial molar volume. What is partial molar volume? Partial molar volume is V1 bar. If V1 bar increases with its concentration, increases with x1. Remember, what we have in here is a solution. That is why we are using x1 here. Okay. So then V2 bar, what with x2? Huh? That is the question. That means, so one hint which I will give is, the V1 bar is increasing with x1, right? That means dou V1 bar by dou x1 increases, right? Sorry, no, x1 is increasing, right? That means it has to do something with this, right? It is going to be positive, right? So I hope the question is clear to everyone, right? So we have a binary mixture containing A and B, and partial molar volume of one of the component. It increases with x1. Now what we need a what is the correlation between a partial molar volume of other component with respect to its mole fraction? The hint which I have given is, it has to do something with this derivative, right? So once if somehow you are able to find what is dv2 bar the dou x2, positive or negative, you will be able to find, right? So this is a hint. So I'll give you a couple of minutes to check. I hope the question is clear to everyone, right? So if anybody has any doubts or question, they can ask now. And others, for those who have understood the question, can solve the question. Okay. Is anybody able to solve it? So anybody would like to answer? Anybody got the answer? The answer is option B, decreases. Right? Correct answer is option B. I can give one more hint. I'll give you one more hint. So how you solve the problem? You use what is called as Gibbs-Duhem equation, right? Use Gibbs-Duhem. Okay. Try again. If anybody would like to that, I'll give a couple of minutes. Anybody got it? Nobody got it? Okay, then let us discuss. No worries, we will discuss. Okay. Okay. What will the answer is option B, that it decreases. So what we have is, we know according to Gibbs-Duhem equation at constant T and P. What is Gibbs-Duhem equation? This is the Gibbs-Duhem equation. Summation xi dmi bar is equal to 0, where m represents any property of the system. The subscript I represents for the number of components, and the bar on m represents it's a partial molar property, right? Xi dmi bar equal to, so when we are saying that this is for volume, so in that case m will be replaced by v. Okay, so for binary mixtures, we can write, we just have to expand this. So basically what? Summation xi dmi for I is equals to 1 to n. So here n is equal to 2 because it's a binary mixture. What we have, summation xi dmi bar, where I is equals to 1 to 2. This is nothing but x1 dm1 bar, right? Plus x2 dm2 bar, right? This is what we have written here for binary mixture. Then what we do basically, let me rewrite it. Then what we have is, we have this expression. Now what we do, so here I have skipped couple of steps, so I will write it down. So what we basically have is x1 dm1 bar. So what we do, we just take this thing to this side, is equal to minus x2 dm2 bar, right? Then what we do, we divide both the thing by dx1, right? dx1 dx1, right? Then what we do, we take this to this side, right? That means what, dm1 bar dm1 bar by dx1, which is this expression, divided by, we bring it here, d m2 bar by dx1. This is equals to minus of x2 by x1. Right? So it should be x1, right? It should be x1. It should be x1. Right? So this is the expression. So what we have is, it has been given that m1 bar. So for v, it will be what? We just have to replace v m by v. So for that also I'm right. So it will be dv1 bar by dx1 divided by dv2 bar by dx2 by dx1, sorry, is equal to minus of x2 by x1. Right? x2 by x1. So it has been given that v1 is increasing with x1, right? That means this is positive, right? This is, it's a mole fraction, it cannot be negative. This is positive, this is positive. Okay, that means, so if we rearrange it, what we will get is dv2 bar by dx1 is equals to minus of x1 by x2 into dv1 bar by dx1, right? I just took this to this side and there's cos multiplied, right? That means, see, this is going to, x1 is going to be positive, we have negative here, x2 is going to be positive, and we are already given that dv1 bar by dx1, v1 is increasing with x1, that means this is also going to be positive, right? That means what we have is dv2 bar by dx1 is equals to minus 1 multiplied by a positive quantity, right? That means dv2 bar by dx1 is what? It's going to be negative, right? It's negative. That means v2 bar is going to decrease with respect to x, right? And that is precisely what is asked. See here, minus multiply, this is going to be positive, this is going to be positive, and this we are already given is that it's positive, increases with concentration. But so what does it imply? It imply, and this is also given to us, both x1 x2 positive. So what is going to be dm2 bar by dx2 is minus 1 multiplied by positive term, which is going to be a minus, right? And hence m2 bar decreases this, so here it has to be x1, right? With respect to x2, so here it has to be x1. So with respect to x2, it's going to be positive, whereas with respect to x1 is going to be negative, right? So molar volume of other component decreases. Okay, so let me just clear the screen, right? Okay, so dm2 bar by dx1, this is x1, it's going to be negative. That means dm2 bar decreases with respect to x1. With respect to x2, it will increase, but with respect to x1, it's going to be decrease. Molar volume of component decreases with the concentration, that is x1. That means yeah, dv2 bar by dx1 is going to be negative, right? Okay, anybody has any questions? If anybody has any questions, they can ask. Meanwhile, I will clear the board. I hope the solution is clear to everyone. If anybody has any doubts, they can ask now. Okay, anybody has any questions? I hear no questions. Neither do I see anything in the chat box. Okay, the correct answer is, let me just clear this one. Right. The correct answer is option B. That is V2 bar decreases with X1. Okay, option B is the right answer. I hear no questions, so I assume that the concept is clear to everyone, and we'll move on to the next question. So this is the next question. So what we are given? We are given vapor pressure of acetone and acetonitrile. Okay, so acetone is component 1 and acetonitrile is component 2. Are this so vapor pressure of acetone is 85.12 kilopascal and the vapor pressure of acetonitrile is 39.31 kilopascal. So what? So with this information given, what we are asked to find is estimate x1 and y1 at the total pressure of this. So what basically we are given is, we have a container having components A and component B, where A is acetone and B is acetonitrile, and we are given the saturation paper pressure of component 1 is 85.12 in kPa. Okay, saturation pressure of second component is 39.31. Okay, and total pressure has also been given. Okay, so these three are different pressure, and these two are the saturation pressure at some conditions, whatever temperature of this thing is, and total pressure is a total pressure. Okay, when we combine the mixture, it will be exerting some pressure onto the walls of the container. So that pressure is 65 Kelvin, 65 kilopascal. Okay, and what we are asked to find? So this is a two-phase system, right? This is the liquid part. Let me just use different color for that. So this is the liquid part. This is a vapor part. Okay, this is the vapor part. Okay, so we have a VL equation, vapor liquid equilibrium with these conditions of saturation pressure, and this is the pressure, total pressure. And we are asked to find what is x1, is x1 and y1, right? So if you once we know what is x1 and y1, we can automatically find x2, right? Although that is not asked, but I'm telling you. And so one thing which you have to remember is, whenever nothing has been mentioned in the question regarding what is like, whether the gas is ideal, whether the vapor is ideal or non-ideal, or it follows this or which law, so you always assume that the vapor is ideal, ideal gas vapor. Okay, and liquid is also ideal, or solution is also, okay, liquid is also ideal. Okay, so this is a very straightforward question. If you have a basic understanding of what vapor liquid equilibrium is, you can even derive the expression for that from straight calculation. What is the condition for two phases to be in equilibrium? If you have an understanding of that, you can derive the expression on which you can calculate, and you can do it. It's a fairly straightforward question. Otherwise, you have direct formula for this, direct expression for this. So I'll give you a couple of minutes to try the question. I hope the question is clear to everyone. Assume, okay, if question is not clear, you can ask. And for those who are doing the calculation, remember to take this. Right? Paper and liquid both are ideal. Okay. Nobody has any question in the question? Any problem in understanding the question, what is asked? Okay, so I'll give you a couple of minutes to solve it. Okay. Anybody got any answers? No? Then I will rub the board and I will start explaining the solution. You can cross check your answer with this. Okay. Okay. So the correct answer is option B. Right? X1 is equals to 0.7344 and Y1 is equal to 0.560. Anybody got it? Okay. You can cross check with your answer and the solution which I am going to give, that you will not make any mistakes. Or you can rectify the mistake which you will make. Okay? It's a fairly straightforward question. So what we are basically given is P1 set has been given to us, P2 set has been given to us, and also total pressure has been given to us. Right? We know these expressions, or we know that for two phases to be in equilibrium, the fugacity of both the phases has to be in equal. Right? Fugacity. Right? On these only, these two expressions will arrive when you do the fugacity calculation and two phase expression. One expression will be this expression, right? And another expression will be this expression. Using this expression only, you will be able to find both these expressions. I'm not doing the derivative part, a derivation of this expression, because it's quite common in and it has been taught in this course. If you refer to the lecture videos, okay. So Pt is equals to P2 set plus x1 into P1 set minus P2 set. Okay, so let me do, for those of you who do not have the understanding of, so this is very clear. For two phases to be in equilibrium, fugacity of vapor has to be fugacity of liquid, right? That is one. And total pressure has to be equal to the partial pressure component plus partial pressure component. Now from Dalton's law, we know that Pt is equals to what? P1 bar, partial pressure of 1 is P1 Pt plus Y2 Pt, right? In this case, Y2 will be nothing but 1 minus x1, right? And what will be the fugacity? Vapor phase, right? Fugacity of vapor phase will be what? Yi of I component is Yipt. That has to be equal to what? Xipt, right? Xi, right? So this is for the ideal, this is ideal vapor and this is ideal solution or ideal liquid. If the vapor would have been a non-ideal, we would have added here fugacity coefficient, right? Phi, and if sorry, let me write it different color. Okay, if the ideal vapor would have been non-ideal, we would have added phi here, and if the solution would have been non-ideal, we would have added activity coefficient here. Okay, but because our both vapor and liquid are ideal, we'll be putting like this. Okay, so now what you do, you substitute Yipt in here. What you get, Pt is equals to x1 P1s plus x2 P2s, where x2 for binary is going to be 1 minus x1, right? So x1 P1s plus 1 minus x1 P2s. There is nothing but Pt. So when you do the rearrangement of this expression, you end up with this. Okay, you club together the x1 terms and x1 terms. So you will be getting this expression. Now you have what is P2 set, you know what is Pt, we know what is P1 set. So this is known, this is known, this is known, this is known. You can straight away calculate, sorry. So for us, this is known to one, P2 set, it has been given, P1 set has been known, P2 set has been known, also Pta is also known. So clearly we can find what is the mole fraction of more volatile component in liquid. It will just rearranging. After rearranging, you'll be getting this expression. You put Pt is equals to 65. P2 set is this. P1 set is this. You end up with x1 equal to 0.560. Similarly, then you use this expression or you use this expression. You get you rearrange it to calculate yi. So p or you can just divide both sides by pt. You end up with this expression and then p. Just now we calculated what is x1, right? Pi set is already known to us. So does the pt. You just put in the known values and you'll be able to get the final answer. So anybody has any doubt in this question? I hope there are no doubts. I don't see any questions. Okay. So I'll just clear the board. Okay. Meanwhile, if anybody you have doubts, they can ask. Else, if anybody would like to write this down, they can write also. Okay. Okay. Nobody has any questions. I hope the solution is clear to everyone. The correct answer is option B. Okay. So we'll move on to the next question. So the next question is this. It's a tricky question. Okay. What we are given? We are given molar density. Remember, it's a molar density, it's not mass density. Okay. Its unit will not be kg per meter cube. It will be something mole per meter cube or kilomole per meter cube or kilomole per liter or something like that. Okay. The molar density of water vapor. Okay. It's a gas phase. At the normal boiling point of water is this. Okay. So the unit is mole per meter. The compressibility factor Z under this condition is closest to what? So the hint which I am giving is, remember what is normal boiling point of water. So this will be associated with P and T. Okay. So if you remember it, then you can use ideal gas law. Or you can use the expression, not the ideal gas law. You can use this expression that PV is equals to ZRT. The whole catch is whether you know what is the normal boiling point of water. Once you get it, you know P, you know V, you know R, you know T, you can calculate Z. Okay. Or even if you don't know, let's first say, you can just convert this 33 mole per meter cube in kg per meter cube. And we know that that the this is the density, and we know what will be the density of water at ideal conditions at this normal boiling point. It will be 1000 kilojoule per meter cube, kg per meter cube. If the density is approximately same, that means Z will be equal to 1. If it is less, then Z will not be equal to 1, or if it is more, also Z will not be equal. So depending on that, so there are so I've told you two methodologies to find it. So I'll give you a couple of minutes to try it. I hope that much the hints are clear to everyone. I'll give a couple of minutes to solve. Anybody has any question? Anybody solved? So I'll give you the answer. The answer is going to be this. Okay. So if you solve by this method, you should get density approximately as 990. Okay. Sorry, approximately as 1000. Okay. So anybody got the answer? I will clear the screen. I hope the question and hints are clear to everyone. I will now start with the solution. Okay. Correct answer is option B. Okay. Okay. So we know that Z is equals to PV by nRT. So these are the conditions of normal boiling point of water. Right? Pressure is 1 atmosphere, which corresponds to this value in Pascal, 1.01325 10 to the power 5. And N by V is already given, right? 33 mole per meter cube. We know the value of gas constant and temperature is of normal boiling point is this, right? 100 degrees centigrade, which is 373 Kelvin, right? When you substitute it, right? Let me first clear the screen. Okay. So when you substitute it, you put pressure value as this. Okay. P by RT, P by V, N by V, P by rho RT. Okay. So this is R, this is the temperature, and this is the rho value. This is nothing but N by V. So you end up with 0.98. Z as 0.98. So if you look at the option, you don't get 0.98, right? But it is very close to 1, right? It is very close to 1. Hence, the correct answer is option B. Okay. Anybody has any question? Anybody who didn't understand? It's a fairly simple. Okay. So this is the expression for that. And using that, you calculate Z as this. So I'll wait for a couple of minutes if anybody has any doubts or if they would like to note down. Okay. I hear no question. So I think the so question and solution is clear to everyone. We'll move on to the next question. Okay. This is the next question. So what we are given is at 25 degrees centigrade and 1 bar of partial pressure. Remember, it's a partial pressure. The solubility of ethane in water is very small. The equilibrium mole fraction is of ethane is this 0.0033. Okay, and at 25 degrees centigrade, the compressibility factor of ethane is given by this empirical relation, where P is the pressure and it is in bar. What is the solubility of ethane at 25 degrees centigrade, but with a partial pressure when the partial pressure is 35 bar? Okay, we are also given that the saturation pressure of ethane at these conditions of temperature and pressure is 42.07, and that of water is this. Okay, so what is to be noted here is that the whole process is being done at 25 degrees centigrade, and what we have a container which has A and B, where A is ethane. Okay, you can call A as ethane and B as water. Okay, and initially this system water 1 bar of partial pressure, right, where mole fraction is this, and the vapor accompanying this solution has a vapor of ethane has this expression, right? Now what we are asked to find is we are asked to find what is the solubility of ethane. That means basically we are trying to find X only, but X2. But here, now although temperature is same, the total pressure now changes to 35 bar. Sorry, the pressure now changes to 35 bar. Okay. And we are also given the saturation pressure of water as well as, or this is of water and this is of ethane. Right. So just by looking at these two saturation pressure, we can say that there is a huge difference in this. Hence, one of the component is going to be present in dilute amount, right? So with this hint, I would like you to try this question. It will have it clear the screen. I hope the question is clear to everyone. If anybody has any doubt, they can ask. I will also give the uh, these are the options. This is nothing but the final x2 values. Right? The x2 is equal to what? Okay. So I'll give you a couple of minutes to solve it. So anybody got it? What is the final answer? So final answer is this. 8.47 into 10 raised to power minus 4. Anybody got it? Nobody got it. This is a bit of a difficult question. Okay, so don't get disheartened if you're not able to solve it. I will share the solution with you. Okay, we know that for two phases to be in equilibrium, the fugacity of those both the of all the components in both the phases has to be equal. Okay, so fugacity of ith component in vapor phase has to be equal to fugacity of ith component in liquid phase. Okay, and in the initial partial pressure was 1 bar. Okay, so since at 25 degree and 1 bar, the solubility of ethane is very small. Right, solubility of ethane is very small. We consider Henry's law to be valid. Right, you know what is Henry's law? Like I said, because the partial pressure of both the things, there is a huge difference. We can say that one is present in dilute amount. This is the hint which I had given. Okay, so we can say that it's in the Henry's law is applicable. Hence, we can equate the liquid level fugacity to this, liquid phase fugacity to this, and vapor phase. Anyways, the fugacity is going to be this for non-ideal phase, right? So then, using this expression and using this, and this expression, we can write this equality, right? Now let the component I be ethane, right? At 1 bar, we know that pi I by is equal to 1 because P set of water is this, right? Hence, we can consider water to be non-volatile at this condition, and hence yi is going to be 1, right? So we just put in the values pi I into pi I into Pt is equal to h into x, and that means we just rearrange it, we get this expression, and then we write the value of how x has been given to us, that 0.33 into 10 raised to power minus 4. It has been given to us. Just put in the value, we get the Henry law constant. Right now, this is, like I said, it's a constant, right? I hope so. Then we'll move on to the next part. Before that, I will just clear this up. So now what we know, I think I need to clear up. Okay. Okay. So what we have now? Now we have gotten the Henry's law, right? Henry law's constant we have got, and we know that at 35 bar, this is the standard expression to calculate the fugacity, which we have discussed in the previous class, right? Last week only we solved quite a few examples on this, right? So ln phi is equal to integral 0 to p z minus 1 by p dp, right? And where z expression for z has already been given to us for ethane, right? We just put in the values, put z is equal to this value, you do the differentiation, you separate out the terms, you put 0 and pressure is going to be 35. You end up with this expression that phi is 0.773. Then you again apply the same expression which we have used here, that fugacity, equality of fugacity. This is the fugacity of the vapor phase. This is the fugacity of the liquid phase. They are both equal because at 35 bar also there is a VLE, vapor liquid equilibrium, right? So now you know what is phi I, you know what is PT. You don't know what is XI, but you know what is HI. Here we calculate it, right? Although this, so as it is a constant, it is not going to change with respect to pressure, right? So you rearrange it, you get Xi is equals to phi I PT by HI. So this is nothing but total pressure, right? Sorry, this is nothing but pressure, right? So this is partial pressure, right? Phi I P divided by HI. So we know phi, just now we calculated. This has already been given. This we just calculated from here, right? Put in the values, you get this as 0.87 raised to the power minus 4, right? Anybody has any question? So I'll wait for a couple of minutes to get your feedback. If anybody has any question, they can type it in the chat box, or they can just unmute themselves and tell. And for those who would like to, for whom everything is clear and would like to write the solution, I'll give you a couple of minutes for you to write as well. Right? Nobody has any question. I don't see any questions in the chat box also. So I hope the solution is clear to everyone. I'll give you 2 minutes to write. Okay. We'll move on to the next question. Okay. This is also a difficult question, but you can try it. What we are given is, we are giving the second viral coefficient of a certain gas is given by this, right? Where A and B are constant. And the change in internal energy for gas is going from at temperature T0 from a very low pressure to a pressure pi would be what? Right? We have to use this expression, right? So what we need, change in internal energy. So remember, as it's a second viral coefficient has been given to us, we do consider that it's non-ideal gas. So don't use the expression for ideal gas, which is del U is in nothing but NCVDT, right? This expression will not work, right? So first, what you will need to do is, you will first need to find what is the expression du for real gas. Yes, real gas. What is that? And once you put it, then you can use this expression, right? So with this background, I hope the question is clear to everyone. If the question is not clear, you can unmute yourself and ask. Otherwise, I'll give you a couple of minutes to solve it. Okay, so these are the option also I have given, right? So anybody got it? I'll give a couple of more minutes to check. Hmm. So correct answer is option A, right? This is the correct answer. Anybody got it? So nobody got it. Don't be disappointed. It's a bit harder. The question is uh, uh, slightly difficult. So we'll start with the solution. So what we know, this is the basic fundamental equation which we know, that du is equal to TdS minus PdV. Okay. Now what we are doing, we are differentiating both sides with respect to P, right? So what we do, dou U by dou P at constant temperature is nothing but temperature is constant, so temperature will come out, and dou L by dou Tp minus we have this, right? Then we use the Maxwell's relation, which is this one. Using Maxwell relation, we rewrite it, right? We change this to this, right? Then we are already given that Z is equal to this. Z is equal to PV by RT, which is nothing but, I think here it should be B, right? Z is nothing but PV by RT, which is nothing but 1 plus BV by RT. So this expression has been given to us where B is this, right? So we just substitute it, we just rearrange it, and then what we get is this: B is equals to RT by P plus B, and then we put the value of P in here, just nothing but this, and then we do the simplification. What we get is this. We get V as this, right? Now what we have simply have to do, we just simply have to take the derivative of molar volume with respect to temperature at constant pressure. We do it, we calculate this also, right? This is just nothing but taking derivatives, partial derivatives we have to take, and then we resubstitute it in this expression, right? We get this, right? Do you, what basically we get, do you 2P at constant temperature is nothing but minus 2A by T square. Now what we have is this, we just integrate it, right? From T is equal to T0 to T from some values of temperature and some values of pressure. The limits are given in the question, and then what we end up with is this: delta U is nothing but minus 2A pi by T0 square, right? Anybody has any question in this? Anybody has any doubt in this question or this solution, right? They can ask, right? So the correct answer is option A. Okay. Anybody has any question? So I'll give you a couple of minutes. If anybody has any question, they can ask. And the other students, if anybody would like to write it down, they can write down as well. So nobody has any question. So then we'll move on to the next question. Okay. This is a very easy question, which we have similar questions we have already solved in previous classes as well. What we are given at a given temperature and pressure. So T and P has been given. A liquid mixture of benzene and tolerate is in equilibrium with its vapor. What we need? Degrees of freedom. So what we do? Degrees of freedom we know gives phase root n minus p plus 2 we add for temperature and pressure. Because here the temperature and pressure are already defined, we have to add minus 2 here. Okay. And what we have? Number of components 2, number of phases only one. No, number of phases also 2, liquid also, vapor also, plus 2 minus, right? So this cancels this. That means the answer is it. Right? Let us check what is the answer. Yes, the correct answer is option A. Right? Like I said, we know Gibbs phase rule where n is the number of components, p is the number of phases, and d of is the degree of freedom. Right? Since here temperature and pressure are specified, we have to add minus 2 here, right? And here number of components are going to be 2, number of phases liquid and vapor. Here also 2 phases benzene and toluene. So n is 2, p is 2, plus 2, minus 2 because temperature and pressure are specified. Okay? Resulting in degree of freedom to be equal to 0. It is option A. Okay. Anybody has any question? If anybody has any doubt, they can ask now. And if anybody would like to write, I will give you a couple of minutes. Correct answer is option A, 0. Degrees of freedom is going to be 0. So, so basically, what does that mean? That means that the condition is automatically fixed. There is only one unique point like this. Right? No question. So I hope that the solution is clear to everyone. And then we'll move on to the next question. Okay. What is the next question? So what we have? A system of acetone and acetone. So we have a ternary mixture here. System acetone, acetonetal, and nitromethane at 353.15 Kelvin has the overall composition of 0.45 of acetone, 0.35 acetonetal, and 0.20 of nitromethane. Right? If you sum it all, it should be equal to 1. Okay. Now assuming Raoult's law. Okay. So what we need to know is what is Raoult's law. Is applicable to the system. What would be the bubble point pressure? Okay. We are given saturation pressure of all the components. Right? It's a fairly easy question if you know what the Raoult's law stands for. Right? What is Raoult's law? And remember, these are the compositions, right? Ah, I'll give you a couple of minutes to sort it. I hope the question is clear to everyone. Right? Fairly easy question. I'll give you a couple of minutes to solve it. And if anybody has any answer, I will ask you. Okay? Him. Okay, anybody got it? What you basically have to do is total pressure is nothing but sum of partial pressure. Okay, P1 bar plus P2 bar plus P3 bar. This is what? X1 P1S plus X2 P2S plus X3 P3S. Right? Where S stands for saturation pressure, right? Saturation. So P1, P1S, P2S, P3S has been given. So this is known, this is known, this is known. Composition has also been given. So you just put in the values, substitute the values, and you will get total pressure. Okay. Let me just erase it out and give you the answer. Okay. The correct answer is option B, 132.4. The answer is in kilopascal. Okay. Like I said, PT is nothing but this. You just substitute the values and you get the final answer as this. Look, very straightforward easy. If only you know. If only you know what Raoult's law is, right? Correct answer is option B. Anybody got it? So I'll give you a couple of minutes if anybody has any doubt or if anybody would like to write it down. Okay, so I hear no question. So I hope that the solution and the question and its solution is clear to everyone. And we'll move on to the next question. This is the question on excess properties, right? So what we have, let us consider a binary solution formed by two components, component 1 and component 2. And if G1E bar, G1E, that is what gives free energy of component 1, excess gives free energy of component 1. Okay, so it is given G1E is the excess gives free energy of component 1 at x1 equal to 0.3. Okay, and G2 excess is the excess gives free energy of component 2 at x2 is equal to 0.4, 0.6 or 0.5. Then what is the ratio between G1E and by the ratio of G1E by G2E, where the activity of the above two components are given as 1.2 for component 1 and 1.5 for component 2. So what is basically given? Gamma 1 has been given as 1.2, gamma 2 has been given as 1.5. Okay, and excess crispy energy at these conditions of mole fraction is G1E, and at these conditions of mole fraction of 2 is G2E. And what we need the ratio of G1E by G2, right? So I hope the question is clear to everyone. And these are the options. Let me first. So these are the options. Okay. So I'll give you a couple of minutes to try. Anybody got it? The correct answer is option C, 1.15. Anybody got it? So let us start with the solution. So what we know that G by RT is equal to summation xi and gamma. For binary mixture, we expand this. What we get is x1 ln gamma 1 plus x2 ln gamma 2. We put x2 is equal to 1 minus x1 because what we have is G1 E bar and G2 E bar, right? So we have for component 1 and component 2 as well. That is why we are putting it, right? We get G E bar is equal to this, right? Then we take the ratio, right? So G1 bar is this one, right? And G2 bar is nothing but this one. Right? Because for the other thing we have been given x2, that is why we are just writing in terms of x2. And first we kept it in terms of x1. We just put in, so it is given that gamma 1 is 1.2 and gamma 2 is 1.5, and G1E bar, G1E is nothing but at x1 equal to 0.3, right? That means x2 is going to be 0.7, right? So this multiplied by this plus this multiplied by this, and G2E bar G2 is nothing but at x2 is equals to 0.5. That means x1 is also going to be 0.15. Okay, so we just put in the value and then we get this expression. Okay. Anybody has any doubt in this question? Okay. This is the answer. Answer is option C. Right. So I'll wait for a couple of minutes. If anybody of you have any question, you can either unmute yourself or you can text me in the chat box. And if nobody has any question, uh, then you can write this down. I'll give you a couple of minutes. So nobody has any doubt. If nobody has any doubts, we'll move on to the next question. Okay. So the next question is this. Okay. So the next question, it is a theoretical question. What we are given the necessary and sufficient condition for thermodynamic equilibrium between two phases. Okay. Just now I said concentration of each component should be same in two components. I don't think temperature of each phase should be same. This is criteria for thermal equilibrium, not okay. So this is what it's not thermodynamic, it's chemical equilibrium. Okay. The question is chemical equilibrium. Chemical equilibrium between two phases, right? The pressure should be same in two phase. No. The chemical potential, yes, because chemical potential will translate into fugacity, right? And we know that fugacity has to be same, right? The chemical potential. So here instead of thermodynamic, it is chemical equilibrium. Okay. The correct answer is option D. So I hope the question is clear, solution and question is clear to everyone. If you have no questions, we'll move on to the next question. Okay, we'll move on to the next question. So this is the question. Okay, so what we are given is, so there it is a link type of question. Okay, so what we are given, we are given fluid component 1 in a binary liquid mixture of component 1 and 2 at 298 Kelvin and 20 bar. So remember, total pressure has been given as 20 bar. Okay, is given by this expression, where F1 is in bar and X1 is the mole fraction of component. What we need, the fugacity of F1 of a pure component. Okay, so this is the, so this is I think F1 bar. Okay, so this is F1 bar. Okay, so this is the fugacity of component 1. So you basically you can say partial molar fugacity, right? So fugacity of component 1 in a binary mixture is given by this expression. Now at the same conditions of temperature, pressure and everything same, if instead of binary mixture we would have had uh, only a mixture of only pure component A. So what is the fugacity of that component is what they are asking. Okay. So I hope the question is clear to everyone. Okay. So I'll give you a couple of minutes to understand and solve the problem. I hope the question is clear to everyone. If the question is not clear, you can ask. So anybody got it? The correct answer is option B, 10 bar. Anybody got it? I'll start with the solution. So what we are given is F1 bar. So this is the partial molar figure set of component 1 in a binary division. Okay, so if you just put x1 equal to 1, what will we get? We'll get F1 bar and x1 equal to 1. That means it's a pure component. That means this is nothing but F1. Right? This is what we want, right? So that means if we just put F in place of x1, if you put x1 equal to 1, what we will get? 50 minus 80 plus 40. It will be what? 90 minus 80, right? This is number 10 bar. This is the answer, right? Because we want F1 of pure component, right? So let us discuss this in a more formal manner, okay? Okay. What we have is when mole fraction approaches unity, the fugacity of component 1 in a solution in a component, fugacity of a component in the solution comes equal to fugacity of pure component. And what we have, let me erase it. F1 is nothing but F1 bar when x1 equal to 1. So in this expression of F1 bar, we just put x1 equal to 1 and we get the value of F1. So this is what 1 is 10 bar. Hence the correct answer is option B. Okay. So I hope the solution is clear to everyone. I'll give you a couple of minutes to write it down, and if in the meantime, if anybody of you has any doubts, they can ask. Okay. Nobody has any questions? Then we'll move on to the next question. Okay. The next question is what we are asked to find is Henry's law constant given for component. Okay. These are the options: 10 bar, 50 bar, 0.5 bar. The expression for F1 is going to remain the same. F1 bar is same as what we have given in the previous above. So let me just rearrange so that you can. So this is the expression for F1 bar. Okay. And what we are asked to find is what is the Henry's law constant. So I'll give you a couple of minutes to solve, to try the question. Okay. Anybody has any answer? The correct answer is option B, 50 bar. Okay. Anybody got it? So let me start with the solution. Okay. So what is given the what is Henry's law? So Henry's law constant is given by this expression. Okay. Limit x1 tending to 0, f1 bar by x. Right. So k1 is nothing but limit x1 tending to 0. F1 bar, what is F1 bar? It is nothing but 50x1, right? 50x1 minus 80x1 square plus 40x1 cube divided by x1, right? So if we put x1 right away, we get 0 by 0 form. So what we do instead, we take x1 common from the numerator and then we cancel it out. So what we basically get is k1 is equals to limit x1 tending to 0 of 50 minus 80x1 plus 40x1 square, right? You put x1 equal to 0, you get 50 minus 0 plus 0, which is nothing but 50. Okay, so what we get is a x1 equal to 50 pi, option B. Okay, I hope the solution is clear to everyone. If anybody has any doubt, they can ask. And if anybody, in the meantime, if anybody would like to write this down, they can write down also. I'll give you a couple of minutes. Okay, I see no question. Let us move on to the next question. Okay, so what we have is fugacity coefficient of component 1, that is phi 1, and activity coefficients are 4. So this is a continuation of the previous question. Okay, previous question. So this is the expression for f1 bar, right? So it is 11 to 13. So we have solved 11, question number 12, and question number 13. So what we want is the fugacity coefficient of component 1, that is nothing but phi 1, and activity coefficient y1. These are, what is the expression for that? Right? So these are the options, right? So I'll give you a couple of minutes to try. Okay. So this is the question. Fugacity coefficient we need to find, and also the activity coefficient. Okay. Anybody got the answer? The correct answer is option A. Okay. Y1 is equal to 0.5 and gamma 1 is equal to 5 minus 8x1 plus 4x1 square. Anybody got it? Okay, so let me try to solve the question. What we have is this is the answer. So how fugacity coefficient? What is fugacity coefficient? It is nothing but ratio of fugacity and pressure. So we already calculated what is fugacity. Fugacity of pure component one is f1 bar when x1 equal to 1. This we already calculated as 10 bar in our first question, question number 11, right? And pressure is already be given as 20. So phi 1 is nothing but 10 by 20. This is nothing but 1 by 2, which is nothing but 0.5, right? Phi 1 is 0.5. Now gamma 1 is what? Gamma 1 expression for gamma 1 is this f1 bar by x1 into f1. Okay, is the actual fugacity divided by the ideal fugacity, ideal solution fugacity, right? So the f1 bar is nothing but this expression, and x1 is x1, f1 is we already calculated 10. So if we divide, what are we left with? We are left with 5 minus 8x1 plus 4x1 square, right? Is nothing but this, is nothing but this. The correct answer is option A. Okay, so I hope the solution is clear to everyone. If you have any questions, if you have any doubts, you can ask me by unmuting yourself, or you can write in chat box as well. So I'll wait for a couple of minutes for you to ask questions, or if anybody would like to write, they can write. Okay. Here no questions. So I think the solution is clear, and then we'll move on to the next question. Okay. This is the next question. Okay. Determine fugacity of pure propane at 32 bar and 333 Kelvin. The molar volume of liquid propane has been given, and we are asked to consider fugacity coefficient of saturated vapor as 0.1, and the Antoine constant for the acetone are given as this. Right? Where the I think this is not acetone, this is propane only. Okay. The saturation pressure is in bar and temperature in Kelvin. Okay. Assume VR does not change with pressure. Okay. I hope the question is clear to everyone. So I'll give you a couple of minutes to solve it. Okay. So anybody got any answer? The correct answer is option C, 19.28 bar. Okay. Anybody got it? Let me try to solve the question. Okay. So what we are given? We are given the temperature as 313 Kelvin, 333 Kelvin, and we are given pressure as this. This is nothing but, I think, pressure is nothing but 32 bar, which when we convert to Pascal, 1 bar is equal to 10 to the power 5 Pascal, right? 10 to the power 5 Pascal, right? That means P is this, and we are given phi as at as 0.91, VL as this. This has all been given to us in the question. We are also given Antoine constant. So with the help of Antoine constants and Antoine expression, what we will do is, so let me first clear this out. So what we are given Antoine equation as this. Okay, we are substituting the Antoine constant for, this is not acetone, this is propane. Okay, for propane or acetone, it's a basically single component mixture. Okay, whatever we have. Okay, so we are given, so this is the Antoine expression. We are given A, B, C, and temperature. We put it in this, and then simplifying, we get the PSAT as this 20.577 bar, and we know that the fugacity is given by the Poynting correct. So this is the expression by which we get fugacity for liquid using Poynting correction factor, and fugacity using Poynting correction factor. So this is not fugacity, nothing but pi sat multiplied by p sat multiplied by exponential of vapor liquid volume into p minus p sat divided by RT. We just put in the value. So pi sat, it has been given, right? 0.91. We put 0.91. P sat, we just calculated 20.577 multiplied by exponential of VL. VL has been given already 73.4 centimeter cube per mole. Then total pressure has been given as 32 bar. That is nothing but 32 3 lakh. Sorry, 32 lakh of Pascal. Right? We just put it in bar. We just put it in bar minus 20.57, which is P sat, divided by 83.14 multiplied by temperature. We end up with a fugacity of 19.28 bar. That is nothing but the correct answer is option C. Okay. Anybody has any question? If anybody has any question, they can ask, or they can write in the chat box as well. And for those who would like to write this down, I'll give you a couple of minutes. Okay. So anybody has any doubts? I see no questions. We'll move on to the next question, which is a very easy and conceptual based question. Okay. So what we are asked, the Poynting correction factor used for the calculation of fugacity of a liquid. Okay. The factor can be neglected if the system pressure is very dash the vapor pressure of the system. Should it be very close to? Should it be very small compared to? Should it be very large compared to? Or should it be none of the above? Okay. So try it. I'll give you a couple of minutes for you to try, and then I'll give the answer. Actually, it's a very straightforward and very easy question. I hope you were able to answer. What is the correct answer? The correct answer is very close, right? The answer is very clear, right? Right. So the answer is, if P is equal to P set, the Poynting correction factor is almost equal to unity. You can look at from here also, right? So if we just put P is almost equal to P set, what will be exponential of 0, right? Is what exponential of 0, e to the power 0. It is nothing but 1. This is what is Poynting correction factor, right? It will come to 1. Okay. So if system pressure has to be very close to saturation pressure, then only we can neglect the Poynting correction factor. Actually, we don't neglect, it becomes 1, right? The correct answer is option A, close to. Okay, we'll move on to the next question. So this is also a linked question. Okay, so what we are given, the constant of van der Waals equation. So this is the van der Waals equation which has been given to us, and we have a binary mixture of butane and octane. So A1, that is for butane, the van der Waals constant at A and B for both of butane and octane has been given. So A1 is 1.58, B1 is 0.145 into 10 to the power minus 3, A2 is 4.23, and B2 is 2.4865 10 to the power minus 3. Okay, what we are asked is we are asked what is the fugacity of N-butane at these conditions of pressure and these conditions of temperature. Okay, fairly straightforward. This is the fairly straightforward question. Okay, so pressure equation of state has been given, where the van der Waals constant has been given, the constants of the equation of state, and what we are asked to do is we are asked to find the fugacity. Right? Remember that how we calculate fugacity. Yeah, there is one expression z minus 1 by p. Okay, dp is equals to ln f by p. Right? So what you can do with this expression, you can find what is the value of z. You can put that value of z in here, and then you can integrate from p is equal to 0 to some p is equal to p. Right? Once you get that expression, you can just rearrange to get calculate what is the fugacity. Once you get the fugacity, you will have the expression for that. Okay, so that is the key part. Once you have the expression, all you need to do is you need to just put in the substitute the values, right? So this is the difficult part, right? So I've given you an hint. So I'll give you, I think, 5 minutes you will require for this, so that you can do the derivation. So the next question is also related to this one. It's better to do the derivation of this, right? So I'll give you 5 to 6 minutes to solve this question, right? Derive it. Remember, so how basically, so I'll explain it again, how you are going to do it. For those of you for whom this is not clear. Okay. So what we are asked to find is we are given equation of state. We are given the parameters of the equation of state. For here, for current case, the equation of state is van der Waals. The parameters are A1, B1, A2, B2. Okay. So and we are asked to find what is the fugacity. So we know that this expression ln f by p, which is the central finding fugacity, right? Is nothing but integral p is equal to 0, p is equal to p, z minus 1 by p dp, right? Where what is z? Z is equal to nothing but pv by rt, right? Or pv by nr, depends on how you write v. Okay. So first, what you do, you rearrange this expression in this form, then you put this in here, and then you do the integration. Once you do the integration, you'll have the expression for ln of f by p. Then you can just take the exponential and rearrange. You'll get f. That is the expression for the fugacity, right? Once you get the expression for fugacity, then what you have to do is you just have to put in these known values, and you'll be able to get it. So here in this question, what I have asked is for n-butane, and in the next question it is for n-octane. Okay, so once you get this expression, you will get two questions answered, right? That is why with this concept you try to solve it. I'll give you 5 minutes, a bit more time to solve it. Okay. So anybody got it? Okay. So after doing the integration and rearranging, what we end up is we end up with this expression. Okay. So this is the value of the integration. Okay. That ln f by p, ln f1 by y1 p is nothing but this expression. So what you need, you just need to substitute. Okay. So these are all the known values. B is given, B is given, B1 is given. So B will be B1 mix. So it will be okay. b minus b, b minus b, right? So we just put in. So b will be for here we are calculating the component one. So this will be b1. This will be b1. Okay. You just put in the known values, and then you'll be able to get the fugacity. The expression is this, and fugacity is this. What is important for you to get is this expression, right? Okay, so what is the next question? The next question is for n of n. Okay. So for doing the calculation of one question, you get two questions for free. Okay. So same expression you have, you just put in the values for the n of n this time. So it will be b2, b2, right? Put in the values, substitute the known values. Okay. And you end up with the expression for fugacity is 4.89. Okay. So I hope the solution is clear to everyone. So I'll give you a couple of minutes to write this expression down, and then afterwards you can try it at home. Okay. So in the meantime, those who have done with writing can solve this question. Okay. We'll move on to the next question. What is the question? Yes. What we are given is, so this is a bigger question. So let me just zoom out. Okay. So what we are given is the following figure, figure A. So this is figure A, this is figure B. Represents the molar property M of a binary mixture as a function of mole fraction of component 1. So let me just do this, and let me just do, can I do it? Okay, so this is x1. Okay, M versus x1. Okay, M versus x1. Okay. Okay. In figure A, so this is figure A, this is figure B. The tangent at point A meets the vertical axis at point I1. Okay, so this is the point. The tangent drawn at this point, so this is the tangent. It meets the vertical axis at x1 equal to 1 at I1 and at x1 equal to 0 at I2. Okay, and in figure B, the tangent drawn. Okay, so in figure B, what we are doing, we are drawing the tangent at point this. The tangent done at this point, it is meeting this axis at this point, and tangent drawn at this point is meeting this axis at point I5. Okay, so the question is all going to be relationship between I1, I2, okay, I3, I4, I5, I6. Okay, so with this information, okay, so we have what we have to do based on the figures, match this one with this two, and select the correct answer using the code given. Okay, okay. Okay, so what we are asked to find, what are the values of I1, I2, I3, I4? So M1, so what is M1? So M is the molar property of the binary mixture. Mi is the molar property of the pure component I. Mi bar is the partial molar component or partial molar property of component I in a mixture. And M1 bar infinity is nothing but partial molar property of I component at the infinite dimension. Okay, I'll give you a couple of minutes to solve it. Okay, okay. So I'm just giving it. So I2, I1, okay, I3, I4, I5, and I6. So I have highlighted the point. So which of them is M1? Which of them is M1 bar? Which of them is M1 bar infinity? And which of them is N? Or whatever we have mentioned in here. So options are this, right? M1, M2, M1 bar, M2 bar, M1 bar infinity, M2 bar infinity. Okay. So which of this is M1? Which of this is M2? Which of this is M1 bar? Which of this is M2 bar? Which of this is M1 bar infinity? Which of this is M2 bar infinity? This is what we have to find. And once you get it, then you can write the answer. I'll give you 5 minutes to solve it. Okay, anybody got any answer? The correct answer is option A, right? A1 is 3. So I1 is nothing but M1 bar. B is 4, which is nothing but M2 bar. C is 5, that is M1 bar infinity. D is 1, that is M1. E is E6. E is 6, that is M2 bar infinity. And F is 2, that is M2. Okay. So let us try to see the explanation for this. Okay. So what we have is M at x1 equal to 1 is nothing but M1, and M at x1 equal to 0 is nothing but M2. So clearly from the figure, right? If you look at the figure, right? So M, this is this, so this is for M1. So this is, okay. Let me just, okay. So hence what we have is D is 1 and F is 2. And for binary mixture, we know that M1 bar is nothing but M plus x2 into dm by dx1. Actually, it can be D or it can be 2 also. Okay. And M1 bar is nothing but, if we this is in terms of x2 and x1. If we substitute this x2 in terms of x1, we get with this expression M into, okay. So figure A shows a representative plot of M1 with respect to x1 for a binary system. The tangent line drawn extend across the figure, intersecting the edges at x1 equal to 1 and x1 equal to 0 at points labeled I1 and I2. As it is evident from the figure, the two equivalent expression can be written for slope of this tangent line, which is dm1 by dx1 is nothing but m minus I2 by x1, and dm by dx1 is nothing but I1 minus I. Right? This is nothing but tangent method, right? So this is what is taught in the first class, right? First class of this solution dynamics, right? Whenever we teach partial model property, this is the first thing which we tell. Second method, right? So when you compare these two methods and solve for I1 and I2, what you get is I1 is nothing but M1 bar and I2 is nothing but M2 bar. Hence A is M1 and B is M2. Okay. So that is why what we are saying is the tangent intercepts directly give values of the two partial molar properties. These intercepts, of course, shift as the point of tangential moves along the curve. Okay. And limiting values are indicated by the construction as shown in figure B. For the tangent line drawn at x1 equal to 0, that is nothing but pure species 2. For this M2 bar is that is the point at which M2 bar is nothing but M2, and the opposite intercept M1 bar, which is nothing but M1 bar infinity. Similar comments apply to tangent drawn at x1 equal to 1, that is nothing but pure species 1. In this case, M1 bar is nothing but M1 and M2 bar is nothing but M2 bar infinity. Right? Okay. Hence the correct answer is option A. Right? Anybody has any doubts? So I hear no comments or no chat. So I hope that the this question was clear to everyone, as also the other questions, all the questions which we have taken till now. Okay. So I welcome you all. So I thank you all for attending this session, and I hope that this session has been beneficial to you. and I hope to see you again in the next class as well, in the next week. By the time, if you have any questions regarding the previous assignments or these assignments, we can discuss it in the next class as well. So once again, I thank you all, and I'll wait. For those of you who don't have any questions, they can leave, and I'll wait for a couple of minutes if anybody would like to linger around and ask some questions. Okay, so a couple of minutes I'll wait, and then those who don't have any question, of course, they are free to leave. Okay, thank you once again for joining this session. Okay, so I see. Uh, I don't see any questions in the chat box, and okay, and nobody's. So I hope that everything is clear. Okay. So it's a good time to close the meeting. So I thank you once again. I thank you all for joining this meeting, and hope to see you again in the next class as well. Thank you. So I'll be stopping the meeting now, ending the meeting. Thank you all.